Good afternoon. I am Jang Hyukjae from the Line Plus Messaging Client Engineering team. My presentation is on the client platform feature, one of the features of the Line Federated Learning feature that was released in October last year, excuse me. And I would like to talk about what kind of issues we can find during federated learning and how they were solved. And if you want to learn more about machine learning, federated learning, and if you're interested in private information protection, please refer to the presentation made by Kikuchi Haruka yesterday. Well, I guess this shows that we're actually on live. Can you please wait? Okay. Yes, so we're on the next slide. So those of you who are here to listen to this presentation, I assume that you are familiar with what federated learning is, but let me give you a brief introduction. Generally, when we say machine learning, we talk about machine learning based on cloud. So the logs we collect via the servers on the cloud, we make the machine learning model learn that and then use that directly at the server, or we send it to the mobile device to provide the features. But the problem is there can be issues of privacy, and also the user can deny the reception of the information. So, as an alternative to this kind of issue, federated learning was created. So, the, the user log is not collected at the cloud, but the model is distributed to the user device, and the log in the device does the learning, and then the model will be collected at the server to create a new model, and then it is sent back to the user device. So that is the workflow. Compared to the cloud-based machine learning, it is better at privacy protection. So after Google has applied Gboard on its keyboard app, federated learning has become more popular, and Apple and Meta is also actively researching federated learning. Naver is also using federated learning on smartboard, and Line is also reviewing the possibility of adopting federated learning. And sticker recommendation for the subscribers, we have applied federated learning. So in the past, we have used the usage history to make recommendations, but now we are making use of the machine learning model. And in the A/B test that was done last October, we have been able to identify an increase of 5.56% of sticker download. But in addition to sticker, there are many features in Line. So we believe that federated learning can be applied to various features in Line. But in order to realize federated learning, there are a few preconditions. For instance, we need to be able to download the machine learning model from the server, and the learned result must be sent back to the server. And we also need to collect the user log to make the model do the learning. And if there are various federated learnings in line, it's probably better to create a platform to provide a common basis instead of creating different federated learning modules. And in a mobile environment where the resource is limited, it could be heavy. So it needs to be able to do on-device training as well. So for instance, if model learning takes place simultaneously, it could eat up too much memory, or it could take up too much battery. and also it could create glitches. So it is very important to control and manage model learning in a single place. So as a result, in order to operate multiple federated learning at the same time, we not only need to be able to provide common features, we also need to create a platform structure for effective and efficient model learning. So in order to provide various federated learning, we have created a client platform and designed an overall architecture like this. So as you can see here, this is the line federated learning architecture that we created, and in short, we call it LFL. So as you can see in the left and right, there is the service area for and also the platform for federated learning and machine learning. And the reason why the structure is divided, it is much more efficient to provide the service, and it consists of four big elements. First of all, on the upper left, there is the feature service server. So in the case of sticker recommendation service, sticker server plays this role. So for each users, it creates a group of stickers to recommend to the users. For the federated learning, each service generates additional models, and those models are called feature models. And within the Line app, the recommendation of the stickers are done or made in the feature service client area. Feature model is downloaded and it is used when the recommendation is made. And thirdly, on the upper right corner, there is the LFL server, which is in charge of distribution, collection, and consolidation of the federated learning model. And lastly, there is the LFL client platform, which is the core of today's presentation. So machine learning model is downloaded from the LFL server, and the Line app receives the recommendation requests to make sticker recommendations, and the user logs are received to conduct learning, and then it is sent back to the server. As you can see in the table, there are three major components in the LFL client platform. What is most important here is the common module, and then there are multiple LFL client modules. In other words, the common module acts as a manager that manages the application modules for federated learning. So even if there are multiple learning applications, the machine learning model and the download and upload of the setting and also learning schedule are managed in a common manner, and the application models for each service does the learning, and so the storing of the machine learning models and setting and the user logs are done here. And so by dividing these different roles, multiple federated learning can be done without any problems. But as the common module manages the LFL application module, there is something that we need to take into consideration. In other words, the dependency inversion principle, which is often talked about in the clean architecture. I've mentioned that common module plays the role of the manager, and in the general case, there is the common module, which is the upper layer, and then the lower layer is the application module, and the common module tends to become dependent to the application module. But because application module is directly related to the feature services in the Line app, if there is a change in the service or if there is an addition or deletion of services, it is directly impacted. So for instance, on the left-hand side, if the relevant service is gone and application B module is deleted, then the upper layer common module will have to delete all of the relevant functions as well. So the frequent changes that happen in the lower module will affect the upper module because of the dependency. If we do an inversion of the dependency, what happens is on the right hand side, we deliberately invert the dependency among the modules, and we can do abstraction through interface. And with the app interface, we can create the applications, and the upper module, which is the common module, will be independent from the application module, and they will not be affecting each other. So then how can we realize based on abstraction? So based on this example, in the commune module, so for instance, the background work that's triggered by the OS will begin, and then it decides which application will be learned. And then the interface through the interface API within the common module, the application will call the beginning of the learning by the application. In that case, the dependency library will be used to approach the application. And in the common module, even if there are no dependency on the application instance, the learning can begin without any problems. So in the dependency inversion structure, application addition and deletion can be done very easily. So for instance, in addition to the premium sticker recommendation, if we need more federated learning, the LFL application, which is already declared, the interfaces can be realized to create a new application module. And when this is added to the platform, common module and also other application modules will not be affected, and the new federated learning will be operated. So until now, I have talked about how the line federated learning architecture and the client platform was designed. Now I would like to talk about how we were able to effectively handle on-device training in the client platform. So in federated learning, on-device training is the most important key point. If we do not operate the model learning within the device where there is only limited resources, the users can feel very uncomfortable, and they can experience inconvenience, and it could also ruin line's reputation. So we have created some preconditions for model learning. So there has to be sufficient battery, and it has to be fully charged, and there needs to be enough storage. Lastly, the user must not use the device. So the key here is the last condition, which is background processing. Up until a few years ago, this was a condition that was very hard to realize, but fortunately, as there is more interest on machine learning, iOS and Android both provide special APIs for this. In the case of iOS, background task scheduler and background processing task APIs are available, and in Android, work manager is the API that is provided. So if the user does not use the device for a certain period of time, and when the battery is fully charged, the background work can be done. However, in the case of iOS and Android, it allows background work to be done for more than 10 minutes, but if the user uses the device again, the work can be shut down with force at any time. So the developer must be aware of this. Now, on a different note, I would like to explain to you about the overall landscape of the federated learning and how model learning is done within this picture. On the left-hand side, there is the overall definition. So there are different devices where the machine learning model is distributed, and within the device, the user log is learned, and then it is collected in the server and consolidated and redistributed. This is the cycle. But if there are no limitations, and if the learning is done continuously, as soon as the model is distributed, the learning is done exponentially. And as a result, in the federated learning model, there can be excessive reflection of the user's impact in a certain period of time. This will reduce the quality of learning for the certain model, and as the user excessively participates in the learning, there is a risk of exposure of private information. So to prevent this from happening, as you can see on the right hand side, there is rollout and uploading limit. Rollout is, as you can see in the formula here, there is the key and there's the hash where the users are divided equally into different groups, and when it's their turn, they're able to participate in the learning. So as you can see in the left hand side, all the users do not join at the same time when the model is distributed. They can be distributed over the entire period and participate in the learning equally. And the uploading limit will prevent the server upload to be done after they exceed a certain number of learning. But from the mobile device perspective, rollout and uploading limit still pose some issues, which is because for model learning, repeated background work is attempted. So, for instance, there are cases where the conditions for starting the learning is not met. So, in the case of rollout, as you can see in the picture, when the background work begins, new rollout values come from the server, and the determination whether learning should be done or not is made here. But if the rollout value is not met and so the learning cannot begin, the background work will be done repeatedly, and it will try to receive the rollout value from the new rollout value from the server. And so the mobile device and the server will actually have excessive load.
And in another case, when the model learning has been successful, then after the learning is done, the result will be uploaded to the server and the privacy information will be deleted by the log. And then for model training, user log should pile up sufficiently. But then, until there is enough user log, the background task is triggered repetitively. Especially, as I have mentioned, the background processing has to be done for model learning, and the device should not be used for a certain period of time. So most of the time, the model training and model learning is done when the user is sleeping. So the log has been deleted during the nighttime. So to allow user logs to pile up, training does not need to be carried out until the next evening or the next night. So if the conditions for learning is not met, then the unnecessary background process could be executed repetitively. To prevent this from happening, we have created a time configuration such as retry interval or train interval. So if the model learning conditions are not met, then the training is attempted after the retry interval. And if the learning had been successful, then learning is reattempted after the train interval has passed. And this is to give enough time for the logs to pile up. So through this configuration, we have reduced the load for the mobile device and the servers. Then let's see the case where there are multiple applications for learning. To schedule multiple application learning, we have to meet all the conditions such as retry interval and training interval for all the applications. And also when we consider the load of the on-device training, the model training, model learning should be performed one at a time. So to schedule the different applications learning, the training duration has to be predicted and forecasted. So the multiple applications learning should not be overlapping. So for example, let's look at this red arrow. Let's say that the application C's learning attempt has failed. Then in order to schedule another learning, then we have to see the situations of other applications. Application A will not have a lot of issue because the training interval is long enough, but application B will be able to start the learning after the retry interval. So we have to be able to predict when that learning can be begun. So the learning time is longer than the retry interval of application C. So the application B's learning ending time has to be captured so that application C's learning time can be scheduled. So this is very complex. But what I'm saying that is when the application number grows, then there are a lot of different situations and many exceptions will occur. So there will be a lot of challenges and complications. So in LFL, we have made took a different angle. So we are not scheduling each application. We create a single task session, and this session is shared by all applications learning. So we have created the interval-based schedule. In a single session, we change the application that satisfies the interval conditions to conduct model training, and the system calculates the shortest time for interval conditions to be met and use that as delayed time required before the next task. So this interval-based scheduling has two advantages. First, we can guarantee that a single model can be trained successfully at each run. So the background task is shared, so this may be so natural. However many applications there are and however complicated interval conditions are, the the minimum delay time can be calculated and the next task will be registered and then everything is completed. So we call this the register and forget method. And so now let's look at how we have created and processed model learning through interval-based scheduling. First, the OS API is used to start the background processes, and the applications filters the interval conditions and chooses the applications to learn. And the priorities and the latest training time are considered to choose the applications for learning. And we compare the server model version and the device model version to update to the latest version. And before we compare the conditions, the latest training time is updated. And there are lots of conditions for learning to be checked: the rollout configuration value, and also whether there are enough logs for learning. And if the conditions are met, we begin the model training, and if the learning is finished, then the latest training time is updated and the result is uploaded to the server. Last but not least, the timestamps and application interval configurations are leveraged to calculate the next delay time, and then we schedule the next task, and all tasks are completed. And I would like to talk about the LFL client platform's machine learning library and application modules internal repository. For LFL on-device training and inferencing, we use Line's internally developed Yuki Federated Learning, which is called YFL library. We have developed it internally because there hadn't been any federated learning library, and TensorFlow PyTorch has too large library capacity, so it was not right for the mobile environment. So we have newly developed a YFL, which is based on Onyx Runtime. Onyx Runtime supports iOS and Android, and the model conversion can be done from TensorFlow and PyTorch, so there are many advantages. So the most important thing is to create a small capacity library. At present, a limited operation and CPU backend are supported at this point, and also it supports local differential privacy. This is about the privacy function, and I think that this had been covered yesterday at the LFL session. So I think that the recorded video will be uploaded soon. So please refer to that session. Inside the LFL application, there is a inferencing model that is used in Line App's feature service, and there is also a learning model that can be used for user log learning. And there is application model management, and there are configurations also managed. Uploading limit rollout and local differential privacy configurations are all related to privacy information. So we have to check whether there isn't any problem with these values. We have to conduct integrity check. And when there is a new version model update, we apply different policies for different updates. For patch updates, there is no change in machine learning model itself, so uploading limit configurations are reset and user logs are maintained. But when there is a major update, the model itself is changing, so user logs and configurations are reset. And Line App's feature service have the additional information and feature model, so there should be an update with the model. And for user log, the minimum number of logs that are necessary for training are capped. And when the number hits the limit, the oldest log is deleted first. And I would like to talk about what I have learned by participating in this LFL project for a year. The Line Federated Learning Project is participated by many different teams. So it was a very fruitful project because we had made many achievements with the participation of many teams. So I would like to express my thanks to all the people who have joined the project. But when these different teams and different organizations meet and gather together to work together, then the complexity increases. The client platform, server, ML, sticker, and lots of functions are involved. So we had to understand these different functions. And because we had these understanding, the project had been facilitated well. So I would like to give one tip. When you are operating this big project, we have to look at the collaboration points. When there is a lot of collaboration between different teams, the direction is not that clear, and depending on what we have agreed upon, different policies will be applied and different directions will be taken. For example, when we are updating the machine learning model, we have to decide on what kind of policies we will have on data deletion and the data deletion scope as well. And test is very important. Unit test is a must. And just like the Line Federated Learning Project, when there are different components all connected, I would like to advise you to create a sample app. For the client platform, it implements a sample app, and the Line app and LFL servers have been abstracted. And we did the end-to-end test. The good thing about this approach is that when we replay with a sample app, we will be able to see if we've got it right or wrong. So I think the developers know why we have to do this. And the background task for model learning requires the device to be at rest for a certain period of time. So in this case, it will be difficult to know whether there is a problem in learning or not. And it is not easy to do tests because tests requires a certain amount of time, hours actually. So you have to check the test tool in case of Android. And for model learning, I think that remote logging will be a good addition. Before release, QA will be conducted, and because of the background tasks, characteristics, errors error logs will be difficult to be acquired. So aside from the error, we need to know why the background task had not been started. So we have to do the remote logging to monitor the internal condition, and test will be facilitated. So with this, I would like to finish my talk, and now we will move on to the Q&A session.
Thank you very much, Mr. Jang. Now we're going to move on to the plus talk. We're going to have a Q&A session, and those of you who are watching can also ask questions on the bottom of the chat screen. You can find the chat window. Iwasebari Futoshi san will be chairing the Q&A session. Thank you very much, Mr. Jang, for the wonderful presentation on the platform. I am an engineer at the R&D division of Yahoo Japan. Thank you very much. Mr. Iwasebari, you can ask questions first. Yes, so you have how long have you been working on this platform, and what was the reason behind this project? Why did you start this project? Well, I guess I said this during my presentation. It's been about a year. Well, in particular, to be more specific, I think the first meeting took place last April, and actual development took place for about a year. And the platform, the reason why we decided to develop the platform, there was no specific reason, but since we began, we had an understanding that this has to be a platform. And I believe all the participants of the project probably have the same feeling. But I personally think the reason why I thought it has to be a platform was within the Line app, there are various features, and federated learning, if we adopt federated learning, sticker is used in one area, but within Line, federated learning will be applied everywhere. So I thought that we need a platform from the very beginning.
Thank you very much. Next question. When there is a problem in the learning model, what kind of reset system or repository system are there, or recovery system are there? When there is a model error, then we can take two approaches largely. So there are about two models. One is about the inferencing model, and the other is the one used for the learning model. So in inference, there is a direct relation to the line app or service. So when there is a error or a deviated result, then we have to respond to it quickly. So when we are applying to the sticker application, when the result is not good, then we may have to enhance the sticker recommendation algorithm through federated learning. If the federated learning result is not good, then we used the previous algorithm to respond to the issue. And second, when there is a problem in the learning model itself, then the local learning result is uploaded to the server. Then the server aggregates all the results of the learning, and then it applies it to the next version. The server aggregates the data and applies to the new model. Then it checks through a system to see whether there is a problem or not. So as far as I know, that is what is done.
Thank you very much. So, for example, rollback. Do you have a rollback system or rollback structure? Well, basically, at the client, for the model, it collaborates with the server. So if there is a problem with the model, the federated learning model is not used. And also at the server, if the problem is resolved, then it could be downloaded. So that is how the rollback is done. Thank you very much.
Well, thank you very much. Next question. There are many devices using Android, but do you see any specific Android devices that incur lots of failure? Well, we consider that part in our development as well. If it's not inference, if we are doing the model learning itself, we did see those cases. But fortunately, the sticker recommendation model is not a complicated model. The GPU-based accelerator is not used, and we use CPU only for learning. So after release, about a month has passed, but we didn't run into any big problem after release.
Thank you very much. Going forward, do you have any schedule to respond to GPU for a GPU? Well, we do not have a plan to support GPU, but the Onyx runtime that we're using right now uh, is accelerated based on GPU to support both iOS and Android. So in the case of sticker recommendation, it does not require much GPU, but if we were to apply federated learning to another service and GPU acceleration is required, then we can update the YF library to support GPU acceleration. That is, I think, the way we will go.
Well, thank you. Next question. I think there will be a conversion with Onyx, TensorFlow, or there will be a case where there isn't enough functions. So how did you overcome these issues? I think this is related to the previous question. So far, when we converted from TensorFlow, we didn't run into serious problems. And if that happens, then we may have to change the model, or maybe we will have to create a function inside the library that we have created. So maybe we will have to choose between these two options. But I think that this is something that we would consider when we're making a new application. Well, that's about it.
Thank you very much.